Variable functions, and that multivariable is referring to what? The multivariable function, what is the words multivariable referring to? What kind of variable? To independent or dependent variables? Independent. So multivariable is saying that we have more than one independent variable. So multiple quantities going in, right? Multiple quantities that we're taking in combination, and we're working on, what is this? Is this a real value or vector valued function? Real valued, right? So you have multiple quantities that in combination produce a value of another quantity, and that's their dependent variable. Okay, and then we're talking about, now we're starting talking about derivatives, partial derivatives of these. So given z of x and y, if f x of 4 comma 7 equals 5 f y of negative 3 comma 8 equals negative 0.5. There we go. So review here. So if we have this multivariable function z equals f of x and y, interpret the meaning of fx of 4 comma 7 equals 5 and fy of negative 3 comma 8 equals negative 0.5. And what I do not mean by this is the rate of change is 5, right? So what does that mean? That the rate of change, the partial derivative with respect to x is 5. What exactly does that rate of change mean? And what does it mean that the partial derivative with respect to y is negative 0.5? Not just, it's the rate of change. What does that rate of change mean? Okay, so try to talk to the person next to you and say that in as clearly and as specifically, with all the details as you can. Practice this. So this is kind of, there's lots of details. So we want to practice and make sure that we've got it. Our minds are well oiled, right? So we fully understand that and can communicate it. So take a couple minutes. Everybody's talking to somebody. Go. Okay, Austin. Tell me what the number 5 means. What does number 5 mean?
So, for every small change in z, the x value will change by 5.
Okay. Do you agree with that? Julia?
So at constant value of y equals 7,
Okay.
as x is varying around x equals 4,
Okay.
z is changing by 5 times the change in x.
So sit. Okay. What do you think of that? So keeping y fixed at 7, given a small change in x close to x equals 4, the change in z will be 5 times that change in x. Yeah? Okay. Ryan, how about the second one?
So, if you hold x fixed,
Uh-huh.
and
At?
you examine a small change in y
Okay.
around 8, you find that z is changing by negative 1/2 times the small change in y.
See what he said? Knocked it out of the park. Did you hear that? Yeah. So fix x to be negative 3. Change y a little bit from 8, and your corresponding change in z will be negative 1/2 times as much as that change in y. Okay, good. All right, so that's just a little warm up there. And then we said we want to understand these. We want to understand these partial derivatives in terms of our four representations of these multivariable functions. So function definition. So where is that? No. There it is. So like taking partial derivatives algebraically. So should we do the partial derivative of x of this one? No, we don't want to waste our time with that, right? So you get lots of practice in web work doing partial derivatives and evaluating partial derivatives. And that's due at today's web work is due at 5. So you have a chance to ask questions in office hours or email me a question. And that'll just be the for Monday. So that'll be the pattern. Mondays web works will be due at 5 p.m. Wednesdays and Fridays will be due at 11:15 a.m. Okay. All right, but I just wanted to show you that graph. So when I turn on this graph, first of all, what kind of thing will I get? What kind of thing is a surface, right? Given an x and y, you get a corresponding z. And so putting all those points together makes a surface, right? That's pretty cool, huh? Like Lord of the Rings, right? So right, so that's why we don't want to find the partial derivative of this, right? It kind of illustrates. All right, but so there's the algebra side of it. You've got the function, you've got the formula. You're going to take partial derivatives. How about you want to do this one? Partial with respect to x is y, and the partial with respect to y is. Oh, you're so smart. Okay. All right. Okay, and so that's that. And then, so in terms of function definition, and then a surface in R3, so maybe we remember we did this one. No, that's the video. This, we looked at what would it mean for a surface to think about the partial derivative. Well, fixing x, right? Fixing the x value. Suppose we fix the x value, x equals 1. No, too dark. Fix the x value, x equals 1, and then we're looking at the contour or the trace on the surface where y changes, right? Let's see that. Yuck. Is that better? Yeah. So fix x so that gray plane is x equals 1, and let y change a little bit, and see what z does, right? So the partial with respect to y, positive, negative, or 0. Here. That's a pretty good view of it. So the partial with respect to y at this point, is it positive, negative, or 0? You should be thinking it's negative, because if you increase y a little bit, meaning move to the right, z goes down, right? Z goes down. So that's the partial with respect to y, partial with respect to z, or sorry, with respect to x. So now we fix y, right? We fix y and we look at the trace of the surface and we look at what z does for a small change in x. Partial with respect to x, positive, negative, or 0? Positive, right? Because if your x increases, z goes up at some ratio of change in z to change in x, and that is the partial with respect to x. Okay, so that's that. Reviewing here. Oh, remember the guitar string function? That's this. Okay. So that was our guitar string function. I think x was, what was that? X was millimeters down the string, and y was time in milliseconds. And so this is that function as a surface, and this is that function as a contour plot. And so this is the point we actually looked at. I think it was 72.5. So 70 millimeters down from the end of the string, and 2.5 milliseconds after it was plucked. This told us, the z value of that told us the displacement of the string. And so then again, we actually calculated the partial derivatives at that point. And the partial with respect to x, positive, negative, or 0. At that red point right there. What do you think? Partial with respect to x, positive, negative, or 0. Negative. So you see there's kind of a, in the x direction, there's kind of a maximum here, and we're on the way down. Do you see that? Coming forward in x, increasing x. There's like a max along this y value, and then we're going down. What about the partial with respect to y? See that's positive, right? It's heading up for increases in y, and we found the numbers. We actually found the numbers and interpreted the numbers last time. Okay, so that's. Okay, so then we were working on table of values, right? And we got into this one. So let's work on this some more. So when this was the heat index function, right? The two independent variables were the actual temperature and the relative humidity, and then the dependent variable was what if the temperature that it feels outside, right? That's called the heat index. What does it feel like? And so when it's 90 degrees with 45% humidity, it feels like what? 93, right? It feels like 93 because that's pretty high humidity. And so it makes it feel a little hotter. And so I think we started by looking at the partial, and we said our index was I. We were looking at the partial of I with respect to, was it T? And we said that was about, we said, all right, keep the humidity fixed. And so we only, with a table, we don't have continuous values, right? We only have what we have to work with. And so in terms of change in temperature, we have change in temperature of 2, right? So for a change in temperature of 2, how much did we say Z was going up? So this goes up 4 and 3. So we said on around 93 degrees, it's going up by, like we averaged those two. And then I think we got, this is the end of class, we got 1.75. And our units are degrees Fahrenheit that it feels per actual change in temperature. We don't want those to cancel out, right? Because this is a rate of change, and those actually are different, right? This is the change in how the temperature feels, and this is the actual change in temperature. So why don't you practice here? Why don't you work out the partial of I with respect to H at that same point. Do it with somebody else so you agree. Did you get this one? No? Zen, did you get this? What's that? 2 over 5? She wants 2 over 5. Because our change in independent, the best we have here is 5. And for a change of 5, we get change in 2. So then that's 0.4. Question?
How would you know which one to choose? Because like the first, it's 80 and 80 and 81. That's just change in 1 for every time.
Oh, because of these green arrows. Because we want the partial derivative when temperature is 90 and your relative humidity is 45. So we're focused right here. Does that answer it? Okay, so 0.4. What does that number mean? Sarah, can you interpret the number 0.4? Okay, pretty good. So when the temperature is fixed at 90, given a small change in humidity, the change in how it feels outside will be, finish it, 0.4 times the little change in humidity. Okay, so now we've been kind of parsing them apart, right? We've been saying let's just focus on the partial of index with respect to temperature and the partial index with respect to humidity. So now what if it's 45% humidity and 90 degrees Fahrenheit, and the temperature changes by 0.3 degrees, and the humidity goes down by 1.8%. Both those things happen. Both happen. So both the temperature increases by 0.3 degrees and the humidity goes down by -1.8%. I want you to predict the new heat index. Predict what you think the new heat index would be. Right? Can you talk to me about a strategy for this? What were you thinking about this?
I was just multiplying 0.4 by -1.8.
Okay, so 0.4 times -1.8. And what does that get for you?
-0.72.
But what is that? Okay, what does that mean? So you got 0.4 times -1.8, and what you get a number. And what is that telling you?
That would be the decrease in temperature.
Decrease in the index due to the change in humidity, right? Okay. What else?
And then I multiplied 0.3 by 1.75.
And what does that get for you?
0.5 increase in the heat index.
Increase in the heat index. Specifically, which increase?
Can you repeat that?
So like you said it was an increase. Why is it increasing? Why is it increasing? Due to what?
Due to the temperature increasing.
Due to the temperature increasing. Okay. So we've got a change in the heat index due to the temperature increasing, a change in the heat index due to the humidity decreasing. What am I going to do with those? What's that? She's asking if we should just add them together. Some are nodding. Yeah, when you agree. So if we add them together, so it's kind of like the net effect, right? It's like the total effect of both these things happening. So we're going to get a change in the heat index from the change in temperature, and we're going to get a change in the heat index from the change in humidity. So we could symbolize that all as what? So what does that whole thing equal? All that is really finding what? DI, right? So right, so we get the change in index from each situation. It should make sense. You just need to add them together. Okay? And what final value do you get for that? Anybody? Just shout it out. What is it? Someone else get that? So about -0.2, the heat index. So the heat index, it feels like the temperature goes down about 1/5 of a degree, because there's kind of a canceling effect, right? In one case, it makes it go up, the other it makes it go down, so we're kind of a wash. So it makes it feel like the temperature went down a little bit, okay? And so then what do you predict for the new temperature? Yeah, you're gonna do what? New I. So there's this principle of new I equals old I plus change in I, right? That should make perfect sense. Take your old value of a quantity, add the amount of change, and that's going to give you the new value of the quantity. So my highly technical terms here. New I, old I equals DI, and so you get 93 minus this. Okay, so we can have these combinations, right? So we can have these combinations of a little change of each, and to get then the total net change of the dependent variable, you're just going to add up the contributions of change from each partial derivative. Is it okay? All right, so let's. All right, so I want you to find both partial derivatives at 82 now. 82 degrees, 90 degrees, 90% relative humidity. So I want you to predict the new I if all right, so at 82 degrees, 90% relative humidity, predict the new heat index if the temperature goes down by 1.5 degrees and the humidity goes up by 0.7%. So you got to do everything. So either do it with somebody else or check your work when you get done. What did you guys get for partial of I with respect to t? Anyone get that? Shout it out. Partial of index with respect to temperature. 3? Okay, I'm just going to believe you. Partial of I with respect to humidity at that same value, same values. 0.3? All right, are we in agreement on those? Do we agree? Yes? Yes? No? Which one do you disagree with? IH. So IH, we're letting temperature stay constant. It's like when we go up 5, we go up 1.5, 1 or 2. So 1.5 over 5 is 0.3. Make sense? Okay, and so then, what do we get for the new I? Just, anyone got a final answer? Nope, the new index. So that's, I think that's DI. You're talking about DI. 86.7. People are nodding. The new I is approximately 86.71 degrees Fahrenheit. Did you guys get that? Yeah. Okay, so this is what's called, we're talking about differentials now. Differentials. So in general, if z is a function of x and y, can you write a general formula for dz? So let's say dz at a comma b, right? So if at the point xy is x equals a, at x equals a, and y equals b. So can you write the general formula for how to calculate the differential in your dependent variable at x equals a and y equals b? Can you do it? Add the two partials together, add the two rates of change together. So we got to think about what exactly did you. If you understood this example, then we're just symbolizing it. What did we do in this? So x equals a and y equals b. That's where we're at, right? That's the values of x, current values of x, and yeah, Simon.
The partial of x at the point A, B.
Right.
Plus the partial of y at the point A, B.
And that gives you dz. So add the two rates together. Add the two rates together, and it gives you the change in z. Is that what you guys did here? You found you took 3 plus 0.3. and that gave you the change in z. Is that what you did? No, right? So here's the partial with respect to t and the partial with respect to h. Yeah, so you take the partial with respect to t, and what'd you do? You multiplied it by the change in t, right? Given any change in t, the change in heat index was 3 times the change in t. So what do I need here? Partial with respect to x times dx. Gotta let x change. We gotta let x and y change a little bit, right? That's going to determine how much z changes. But what's also going to determine it is what the rates of change. So 2 things going on there. How much you change by. So partial AB times dy. So that should make perfect sense with how you whipped out this example. You did great. Like you knew everything you need to do. But so this is the same thing. You're going to do the partial with respect to x times dx. That's what m dx gives you a little change in dependent, and then m dy gives a little change in dependent, and we're going to add them together. So that's our differential of z. Okay, so now let's talk about contour plots. Partial derivatives contour plots. So here is a function, and this is the what is this? Wind speed. This is the wind speeds in a volcano. So one of the wind speeds in miles per hour. So I should really have this. Wind speeds. So depending on how big the tornado is and how far you are from the center determines your wind speed. So this is a graph of that. So look at this point right here. So interpret that point right there on this contour plot. Can you interpret that point right there? What does that point on this graph mean? Yeah, Griffin.
This is at 200 feet from the center, and the volume of the tornado being 2 million cubic feet.
Uh-huh.
Your wind speed is 75 miles per hour.
What do you think? Yeah, right, exactly. So this point means, so independent variables, size and distance from the center. So when you have a 2 million cubic feet volcano and you're 200 feet from the center of that volcano, the wind speed is just a little bit greater than 75, but 75 is, we're just estimating, so perfect. All right, so now what about so we can say that the wind speed is a function of W equals F of V comma D. So that's this function that we have. W stands for wind speed, and then it's a function of volume of the tornado and distance from the center. So I want you to, can you predict FV of 2 comma 2 and FD of 2 comma 2? How would you do it? So rather than me tell you, talk about it, figure it out. So I want the partial derivative of the function f with respect to v at 2, 2, and the partial derivative with respect to d at 2, 2. You could have done that. These gray lines are 0.5 apart. So this is approximately what? What will I do? So how much the wind speed changes for a change in volume. So how much does the wind speed change from there to there? No, how much does the wind speed change? 25, right? So your change in the dependent variable now is you're going to be looking at the level curves. and pulling the values off the level curves, right? So the change in wind speed is from 50 to 75, or plus 25, for a change of about 0.7, right? This is just estimating, right? This is 0.5 here and a little bit further, right? So this is distance of 0.5 between the lines. And then it looks pretty consistent on this side too. For the same increase in 25 miles per hour, that's the increase of 0.7 million cubic feet. So to me, this looks like about an increase of 25 per increase of 0.75 or 0.7. We got that? 35.7 units on that. What are the units? Miles per hour per million cubic feet. Miles per hour per million cubic feet. Okay, this one? So now we're talking about what? So that's about, so everyone could do this differently. But the point is, you're trying to estimate that around that point, what your change in z, or the change in the value of the level curves is per change in your whatever independent variable you're looking at. In this case now we're looking at fixing volume and changing distance. So here, what? This is about half of 100 foot to get what? Down 25, right? This is 125 here. Oh, this is 100 and this is 75. And then, but on this side, what? So maybe, so we're looking at changes of 25 in wind speed, and we could just average these two changes on either side of the distance. So this is like, what, half of a half, and this is a whole half. So what is that, what, 0.3, 0.4, something like 0.35 or something? All right. So this is like 0.25 and 0.5. So what is it? So, and then how much is our change in wind speed is? Minus 25 for, we need to come up with something. So I'll say 0.4. On this side, it's like 0.3. On this side, it's like 0.5. So split the difference. For a change of 0.4, we're looking at wind speeds going down negative 25. And that is? Quick. Negative 62. What's negative 25 divided by 0.4? Thank you. The units on that is? Miles per hour per 100 feet. Miles per hour per change of 100 feet. Okay, so now I want to increase the volume of the tornado and the distance from the center by equal amounts. By equal amounts. And I want to know what is the change in wind speed. So dV and D, I should have used capital D. So say 0.1 for both. All right, and so look on the graph. So now I want to take a visual aspect to this. Do you see that increase, if I keep them in equal amounts, that's along this line right here. Do you see that? And we said that what? That would be then f of v times dv plus f of d dd But I don't, so, okay, so what I'm interested in now is I want to get the rate of change. Would you agree that there's some rate of change of wind speed along this? That if I increase dV and dd by equal amounts, that there's some rate of change of wind speed that has that combination of changes of v and d. Do you see that? Okay, and so that rate of change would be what? Like per unit length of 1 along that line, right? So like if this were to change by 1 along that, in that direction, then that amount of what? That amount of change of wind speed would be the rate of change now in that direction. Does that make sense? So really we want, check this out. I can write this as a dot product of what? A vector with the partial derivatives and a vector with the differentials. But if I want to get the rate of change, then what has to be true about that vector, the dv dd? I want to get the rate of change along that direction. What has to be true about that vector right there, the dv dd? What's that? Yeah, we want it to be a unit vector. Okay? So if we're talking about direction, then I can throw an angle on there. So what angle are we talking about? Yeah, and the example I gave is 45, but that angle could be anything, right? And what's the unit vector in the direction of theta? But any direction theta. Yeah, that's right. That's right. Yeah. So wouldn't it be cosine theta, sine theta would give me that change in v and that change in d such that this would be a unit vector. Do you see that? Because that'll have a magnitude of 1. That's on the unit circle, right? So what we can do is now I can pick any angle theta and create the vector cosine theta sine theta, which will be the proportional change in v and change in d in the direction of theta to make a unit vector of 1. You see that? And if I dot that then with this vector of the partial derivatives, that's going to be the rate of change in the direction of theta. Where theta is going to indicate some unique ratio of the change in v to the change in d, and then cosine theta sine theta will be the unit vector of that. So we've talked about the fact that with these multivariable functions, two variable functions, there's two derivatives, right? There's the partial with respect to x and the partial with respect to y. But we can really think about how many derivatives. We can think about now combinations of those, right? Combinations of change in x and change in y. So really we can think about a derivative in every direction from the point in question. Not just the x direction and the y direction, but by making combinations of our changes in x and y, we can get a rate of change heading in any direction, or for any combination ratio of change in x to change in y. And that's called directional derivative. So directional derivative means there's an infinite number of rates of change, depending on the ratio of the change in x to change in y that you pick. And so you take the dot product of a vector of partial derivatives, dot, this is the unit vector in the direction of theta. And when you dot those together, you get a rate of change, the rate of change of z in the direction of whatever theta points. We'll pick it up there next time.